Thank you. Good morning. Thanks everybody for joining. And like Melissa said, we'll be talking about some magnetic sensing technology this morning. There's a lot to talk about, so I will jump right in. Um, I'm going to start with just a few slides that kind of set the stage. At MPS, we're a little biased because we generally make position and current sensors. And those are two of obviously the most prolific, the two of the most prolific um, applications of magnetic sensing. So for position sensing, we're generally looking at often it's really angle sensing. Position sensing could be, if I've got a magnet at the end of a joystick, and I want to get away from the old style potentiometer. This magnet may move in three axes, but a lot of times it's really just rotating, and we care what the angle is. And so maybe this is attached to a motor shaft or a knob or something like this, and it's rotating. We want to know what the angle of the field is. For current sensing, it's also pretty straightforward with a current. There is any current has an associated magnetic field. Um, we use the right hand rule. If you point your thumb in the direction of the current, the magnetic field curls around in the direction of your fingers. And that magnetic field strength is proportional to the current density. And then obviously where you measure it as you go farther and farther away, the magnetic field dies off. Um, there are obviously plenty of other types of magnetic sensing applications. We use it a lot in the lab. Everyone's phone has a solid state compass in it for navigation, where we sense the Earth's magnetic field. Medical uses it. Even music, a guitar pickup is essentially just a magnetic sensor. There are more than I could list, but these are the basics, right? That's why we care about magnetic sensing. And today I'm going to focus on position and current sensing, again, because that's kind of what we do. Um, a little bit about magnetic field basics. Um, every point in space has a vector associated with it. So we have what's called a vector field, and that field is what we would call the magnetic flux density or the magnetic field strength. Um, Normally, when I talk about this stuff, I'm going to be I'm going to consider B, the magnetic flux density, to be the quote unquote fundamental field here, because we can't put a sensor inside a material. I'm also going to use Tesla's, the SI unit. You'll also commonly see Gauss on some data sheets. One Tesla is 10,000 Gauss. Um, and at each point, we can take that field vector let's just give it an arbitrary number of, let's say it's 30 millitesla in some given direction, and we can break it into its three orthogonal components. So we've got a by, a bx, and a bz that you can vector add to achieve the overall field vector. Um, some sensors only tell us the direction of the field. So some sensors will only tell us like, hey, and it could be projected onto a single plane. So for instance, if I've got a sensor that just has vertical Hall cells in it, I just am going to know what the direction of the field in the XY plane is. Or some sensors may just tell you the uh, amplitude of the field in a given direction. If I've got a single linear Hall cell, it's just going to tell me, depending on how I place it, it may only tell me the amplitude of the Y component of the field. Some sensors will even tell us the direction and the amplitude. And so we just want to keep that in mind today as I'm talking through sensors, um, whether they're looking at the direction of the field, the amplitude of the field, or both. Lastly, I'll just mention Encyclopedia Magnetica. This is where I got this table from. It's an really nice online magnetics source. And it's got a good treatment of magnetic terms and variables and some of the confusion that's been created by conflicting usages in past literature. These terms were the bane of me when I was in college. What's the difference between H and B? And you'll often see people call B the magnetic field strength, and um, we're starting to see a push in the field to start to correct some of the ambiguity that's been present in the past and standardize terms, and I think even start to eventually standardize units to the SI units. So. That's what I'm going to use today, and whenever I'm talking about field, I'll be talking about the B field, the magnetic flux density. All right. Lastly, before we really get into it, there is one other caveat, and that is sometimes, and I hope I make it obvious, and if not, feel free to ask the response, and sometimes we're going to be talking about the
Hey,
saturated.
Ted, your audio cut out there for a second.
Shoot, this is a problem that I have been having, and I thought I fixed it, and I apologize. So, uh, so this graph is showing me the standard response of a magnetoresistive sensor. So a magnetoresistive sensor will saturate, and it does have a linear region around zero. And sometimes we'll be talking about that linear region. We'll be talking about using a magnetoresistive sensor in the linear region. Sometimes we'll be talking about it in the using it in the saturated region. Hopefully, it'll be obvious by context, but in general, you'll often see when I talk about current sensing, we're almost always talking about using the sensor in its linear region. And when I talk about the magnetic field range, I'm usually talking about the linear range. And when I'm talking about position sensing, I'm often talking about using these parts in saturation. Again, I'll try to make it clear, but I think it's good to keep that in mind um, throughout the presentation. That being said, let's actually jump in to Hall effect. So we're going to start a discussion on the sensors that are have the oldest and still the most widely used magnetic sensing technology, Hall effect. And we're going to start with silicon-based Hall effect because that's the most common. Um, basically, uh, you've got a plate that's built onto silicon. And this is a pretty simple device in conception, at least. The devil's in the details, as they say. But conceptually, what you've got is a plate where we're going to run current through the plate. So here I'm showing our current is being pumped in through the top, and it's going to run down to the bottom of the plate. And as I apply a magnetic field in this orthogonal direction, and here's where you can see the current's going down, this magnetic field is going from left to right here across this Hall sensor. It's going to create a voltage differential because these carriers that are moving across this plate are going to be deflected by Lorentz force. And you can use Fleming's left-hand rule. We love hand rules in magnetics and electrical engineering to determine what direction the force is in. But in any case, it's coming kind of out of the screen. And so you get these electrons that are going to get pushed over to this side, and the holes or the positive carriers will get pushed to this side, and it creates a voltage. So the important thing here is that Hall sensors are fundamentally voltage generators. Sensitivity is going to depend on carrier density, mobility, and thickness. And so that is why material choice matters. That's why, if it was up to us just from a physics standpoint, we actually wouldn't use silicon. It wins because it's easy to integrate all the other stuff around it. We'll see later that there are much better materials that can be used that still use this Hall effect. But it wins because it's cheap, it's reliable, and it's easy to integrate everything around it. Let's take a look at the structure in silicon here. So there's two types of Hall devices. The most common is what we consider a planar Hall device. And there is also a so-called vertical Hall device. Look at this as though this surface is the surface of the silicon wafer. And so here again, this is the surface of the silicon wafer. In a planar Hall device, it's exactly what we talked about before, right? I'm going to inject current into the left side. It's going to come across to the right side. And if I have a magnetic field, magnetic flux density, or B field, that is in the up or down direction, it's going to deflect those carriers, and I'm going to generate a voltage that is proportional to the current source, which we know because we control it, and the B field. And so my voltage, depending on how much there is, I know what the B field is. Vertical Hall device works very much the same, except that now the sensitive axis you can see is across the plane of the silicon. So for instance, if I wanted to make a 3D sensor, I would put one planar Hall device and then two orthogonal vertical Hall devices, one here, and then I'd put one in this direction, and then I can sense all three directions. Here, same thing. We're going to inject current into the center. These are just conductive. This is literally just a metal layer, and then the deep in well. We're going to inject the current. It's going to come out both sides equally until I have a magnetic field, and then that's going to change the current density on one side or the other and generate a voltage. Um, in Hall sensors, offset really matters more than noise. So we apply what's called a spinning current technique. And what that is that in time, so here I'm showing the current going in and coming across. But you notice all of these devices are symmetric. This is symmetric in four axis. Sorry, this is four-way symmetric. This is at least two-way symmetric. What I can do is I can change, instead of injecting current into this conductor and coming across, I can then MOSFET commutate and inject current into this one. And so here, then we get current in, current out, and the voltage now I'm going to measure across these two plates. And then I can inject current this way and bring it across this way. And my voltage will be opposite, but I know that my current's opposite too. This is called current spinning. It's one of the reasons modern Hall sensors are so good. We're not changing any physics, but we're changing geometry and time to eliminate offset and to eliminate drifts and any potential defects that might be in the Hall device. Current spinning. Okay, the next step towards a little more sensitive sensor is going to be to use a 3-5 Hall sensor, so called because it's made of not silicon, but a element from group 3 and an element from group 5 on the periodic table. Here I'm showing gallium arsenide and indium antimonide. These devices use the same Hall effect, the exact same physics. The difference is the material, and that difference can give you a large jump in performance. So you can get about 5 to 10 times better sensitivity and a 10 times better noise floor compared to silicon. But the linear range and the bandwidth are unchanged. So, and when I talk about noise floor, and you're going to see me talk about noise a lot, it's because it's the easiest way to compare apples to apples. What that really translates into is higher resolution. The lower the noise floor, the more resolution you get out of your sensor. So, these guys are not a new sensor class by any means. It's the same class, just better raw physics underneath, and you see why. It's all about electron mobility. So silicon has about 1400. The units here, I don't expect anybody other than the physicists in the group to care much about what this actually means in terms of physics. But the higher the electron mobility, the more sensitive the part. Normally, in industry, we're going to be talking about gallium arsenide. Indium antimonide, actually, there are some commercial parts I found that use this, but it is quite expensive. It's much harder to grow the crystal, and it's actually physically brittle. I did see an article, an interesting article, where someone was using these in the lab, and they're very, very sensitive, but they're also quite fragile and quite expensive. Gallium arsenide is something that's commonly used in the industry, not just in Hall effect sensors, but it's in LEDs. And I think they're even starting to build MOSFETs out of gallium arsenide. Here, we're going to compare again, when I try to go apples to apples as much as possible, are silicon crystal, and you can see that it's the crystal actually looks very, very similar for gallium arsenide. Sensitivity low to medium. Yeah, gallium arsenide, the sensitivity is high. Again, it's 8 times higher. It's directly proportional to that electron mobility. Noise, micro Tesla per root hertz, and you'll always see us say per root hertz. That's how we measure noise. In Hall, well, we're always talking about at a specific frequency. The good news is in Hall, this is white noise, almost completely white noise. So it doesn't matter what frequency it's microtesla per root hertz per 1 hertz, but it's the same noise at 100 hertz or 1,000 hertz because it's white noise. So we don't have to care what set point we're at. The noise for silicon, order of microtesla, gallium arsenide, order of 100 nanotesla. So we're talking about at least a 10x improvement in noise. This is the big one. Integration. For silicon, it's simple. You literally take the same substrate that you're going to put all your MOSFETs and your registers and all your other semiconductor devices on and build a Hall right into it. With gallium arsenide, you can do that, but it's very, very expensive. And so what happens in practice is you've got your silicon with all your FETs and registers and everything, and then you take a second die and build your Hall devices, and then you connect. So these are almost always going to be dual die devices at least. Subsequently, very low cost for a Hall. It doesn't take up much die space. And for gallium arsenide, at least, medium cost, we'll say, less than like a TMR, certainly less than one of the more exotic 3.5, like talked about the indium antimonide, but uh, the cost comes from the fact that you need at least a dual die. And then temperature robustness, Hall, you can't beat Hall for temperature robustness. Gallium arsenide, because of that higher carrier mobility, is going to have a little bit higher temperature drift as well. The choice isn't about physics. If it was, 3.5 would always win. It's about integration and cost. All right. From there, we will jump into magnetoresistive sensors. We'll talk about AMR, GMR, and TMR. This is anisotropic magnetoresistance, giant magnetoresistance, and tunneling magnetoresistance. And these are in order of kind of when they were discovered and put into industry. So historical order is AMR came first, then GMR, then TMR. And we'll start with AMR sensors. So this is the first step away from a classical Lorentz force physics like we have in the Hall into spin-dependent transport. And I say spin-dependent, this all magnetoresistive sensors depend on some type of quantum effect. Um, AMR is this anisotropic magnetoresistance. It depends on basically the spin of the electrons that are traveling through the material. The material itself um, and the important thing about AMR is that it doesn't measure field strength directly. It's going to measure the direction of the magnetization. So you'll generally see it used more in angle sensing and not so much in current sensing. Um, Essentially, if our current, if we're pushing the current through this material at a direction that is orthogonal to the magnetization, and this is magnetized by the external field, then we're going to get a very low resistance and a very high current. Obviously, oppositely, if the magnetization direction of the material, the external magnetic field drives the material into magnetization in the same direction as the current, we get a very high resistance. Um, Compared to Hall, AMR is going to buy you roughly 100 times better resolution, but at the cost of a much smaller usable field range. So, like we say, there's always trade-offs. Oop, can't I move? There we go. Uh, so magnetoresistance ratio, 2 to 4%. sensitivity of 1% to 10% per millitesla, and noise density 10 to 100 nanotesla per root hertz. If you remember, we were in the microtesla range per root hertz for a Hall, a silicon Hall, and yeah, hundreds of nanotesla root hertz for 3.5 Hall. Here, we're even better on noise density. Linear range is quite small, 1 to 10 millitesla, and it's got a relatively low offset drift. Okay, couple things. AMR saturates really easily in stray fields, and once it's saturated, it's no good. It's got a limited dynamic range. It requires magnetic biasing, and this is the big one. The offset can jump after a large field exposure. These also require something that a lot of data sheets often hide. AMR sensors need to be periodically retrained magnetically. Otherwise, your offset and sensitivity can wander around, and they do that by putting generally what they call a set reset circuit in there. And to utilize the set reset, you essentially have to find a time when your sensor's not working because it will not give a valid output when you do this, and you gotta ping it with a electronic. It's an electronic pulse, but it translates into a magnetic pulse, and reshift all the magnetic domains and realign them. And this, I would say, is probably the biggest weakness of AMR. The next step was GMR, giant magnetoresistance. This is a discovery that completely changed magnetic sensing and also hard drives. It's the reason that spintronic exists as a field. Um, GMR doesn't measure force or voltage again, like the Hall sensor. It measures how easily spin polarized electrons can pass through stacked layers. This time, we're not driving the current through the ferromagnet. We're driving the current through a thin layer that's sandwiched in between two ferromagnetic layers. Um, the layers are called the pinned layer and the free layer. The pinned layer gets its name because regardless of the external magnetic field, it tries to stay pinned in the same direction. So it's got a preferred magnetization direction, and it stays there like a hard magnetic material. The free layer will rotate with the external magnetization. And when that magnetization is parallel to the pinned layer, you get a high current, a low resistance. When it's opposite, when it is going against the grain, essentially, then that resistance becomes very high and the current becomes very small. Um, so that pinned layer is giving us a reference direction, and the resistance will tell you the relative angle between these two layers. All right, now we're at a magnetoresistance ratio of 5 to 20%. It's about double or more where we were with AMR. Sensitivity 5 to 20% per millitesla, higher sensitivity than AMR. Noise density 5 nanotesla per root hertz to 50 nanotesla root hertz. This is a big jump. So 5 to 10, roughly, 5 to 10 times more signal, noticeably better noise performance. And offset drift is a little worse than AMR. You're going to see this. Each generation trades robustness for resolution. It's kind of the fundamental MR story. And so as we jump generations, you're going to see this offset drift. They're more sensitive to temperature. They're more sensitive to everything. Almost no GMR sensor is used raw. You're going to always see bias magnets or exchange bias layers in order to create a usable linear region. When I talk about exchange bias layers, this is a very simplified diagram. 3 layers, right? I've got my pinned layer. These are almost always multiple layers, especially the pinned layer. We could give an entire webinar and plus on the stacks of materials that are used to build the pinned and the free layer. It's an entire materials science course, and so that is part of the complexity trade-off that you see. Um, there's also we're going to start to see this recurring theme with the MR sensors, which is the better the sensitivity they are, the more fragile they become in real motor environments. And that's because when you have the higher sensitivity, stray fields affect them more. You just you'll and again I simplify these things to keep this within a 1 hour webinar, but there's systems built around all of these raw sensors to make sure that we try to cancel out um, all the limitations. All right, and then lastly, we have our TMR sensors. This is probably the most advanced solid state magnetic sensor you can buy today, and it's shipping in the millions in plenty of industrial and automotive systems. Here, we no longer have scattering, we have quantum tunneling. So this barrier, this insulative barrier, which may seem a little anti-intuitive, right? Why would we have an insulating barrier when we're trying to drive a current through? It's because it's so thin that electrons literally tunnel through it. The metal tunnel, we call this the metal tunnel junction. It's the fundamental building block of a TMR sensor. But you will also see, like I said, entire systems built around this. You have bridges, biasing, temperature compensation. There's all kinds of system engineering that happens around this core device. Basically, similarly to GMR, we've got a pinned layer and a free layer. When the pin and free layers are parallel to each other, when they're going in the same direction, the current is at its maximum. It's the lowest resistance. The difference is that instead of having the current come through this way, the current is going top to bottom. It's going through those layers and literally tunneling through this insulator film. How easy it is, the probability of tunneling is highly increased when these layers are pointing in the same direction. When they're pointing in opposite directions, the probability of tunneling is very low. And so same thing, we'll see as this free layer rotates with the field, you can determine the direction of the field based on how much current is being let through. Magnetoresistance ratio of 100 to 300%. This is an enormous jump. TMR produces 10 times more signal than GMR, and that's why you generally see it's replacing GMR in precision encoders now. But these numbers explain both the power and the fragility. Phenomenal resolution, very small usable field window, zero point 0.1 millitesla to 1 millitesla. Like I mentioned, almost all modern TMR sensors are really just mixed signal systems with heavy digital correction inside, built around this tunneling magneto junction. Um, yeah, there's a lot of biasing and linearization that happens. Again, this is a very, very simplified diagram. And what you'll see in real life is 8 layers or more of materials that you've never even heard of before or that don't make any sense. But when you stack them together, you get a lot of very, um, you get a lot of very, I'm trying to think of the right word, specific magnetic properties that are desirable. Um, Narrow linear range, easily saturated. This is probably one of the biggest issues is when you have this small linear range, you have to be very careful that external fields don't saturate. And it's something where you can actually damage the part with high field exposure. So MPS has a magnetic angle sensor, the MA600, that uses TMR. And on the data sheet, we say don't expose it to more than 200 millitesla. Now, 200 millitesla is a lot of field, but if you do, you can actually damage this pinned layer or re-magnetize this pinned layer, and then you get INL issues and resolution issues. All right, so let's take a look now at all 5 of these technologies and try to do an apples to apples comparison. Here I'm talking about using this in saturated mode. So this is more angle sensing focused. And the important points here are what's the typical field that we're looking for. Now in saturation, remember I said in TMR, it's a zero point 0.1 to 1 millitesla. Well, that's for linear. In saturation, we're going to be like 1 to 15 millitesla. Silicon Hall, usually 20 to 100 millitesla. Gallium arsenide, about 4 times less, 5 to 30. AMR, 1 to 2 millitesla. GMR, 2 to 8. And these are numbers that are typical, but you've got multiple companies that make these technologies, and they all have their own special secret sauce, and a lot of this depends on those layers and what they actually do and what their sauce contains. So take these with a grain of salt for sure. This is important. The angular response is important. So for silicon, well, not even silicon, just for Hall in general, you get a sine and a cosine, right? You're going to build two orthogonal Hall cells, and one's going to give you the sine, one's going to give you the cosine. GMR and TMR are basically cosine. AMR has a very um, specific problem, and that is its cosine squared. Remember, AMR cares not if the magnetization is in the same direction or opposite direction of the current flow. It's if it's in the same direction or orthogonal. So you can only determine half. You need to build a big bridge and some biasing to be able to determine a true full angle with AMR. GMR and TMR, you only need 2 parts. Silicon and gallium arsenide Hall, you need 2 parts. AMR, you actually need 4 at the minimum. And then notes. I think this is, I don't want to be the guy that reads through the slide, but we'll have a copy of this available after the webinar, and that way you kind of have your apples to apples comparison chart that you can reference. Same technology comparison in linear. And here you start to see um, here's where noise floor really, really matters and DC accuracy really, really matters. So 5 to 200 millitesla typical field range. Uh, Gallium arsenide 30 to 150, 1 to 5, 2 to 10, 1 to 5. You see for XMR, it's a very small, much smaller linear field range. Noise floor is the most important figure of merit here. So you just see it decrease by here 1 to 10, 0.3 to 3. So 3x increase going down to a 50 to 200 nanotesla. That's 100, sorry, a 10x decrease, 2x decrease in the noise floor, and then another 4x decrease in the noise floor. So this is in order of lowest to highest resolution. One important point is because these are white noise devices, you can really filter these quite easily and get even more resolution, but at the trade-off of dynamic bandwidth. And AMR, GMR, TMR are more pink noise, so that means 1 over F noise. They are not as easily filterable as Hall devices. So this is kind of you get what you get. Here there is at least a trade-off where you could trade off dynamic bandwidth for extra resolution by building basically like a sliding, moving, averaging window filter. All right. Last thing is we're going to talk about one technique because I think I've mentioned many times here, hey, you can saturate these parts in external fields. And for instance, if you're in a motor and you've got um, some some stator field that is leaking, you can saturate or you can rebias these parts. One technique that we use here at MPS for a lot of our parts, if you look at MA 900, MA 980, MAQ 79010, We use what we call a differential technique. And so I'm going to explain that briefly here. This differential technique is used to completely cancel out an external field. So this is something that is used only, well, I shouldn't say that. I was going to say used only in the context of angle sensing and not in current sensing. But actually, you can use this in current sensing as long as the current sensor has a current path in it. In other words, you can't use this for field, but
Hey,
you can.
Ted, your audio cut out there. Could you
Hi,
repeat that?
yeah, yeah. Welcome to technologies. Thank you for letting me know. Okay, so I was talking about this differential technique and how this is most commonly used in angle sensing. It can be used in current sensing if the current travels through, if we know that the current is traveling through our device. But it cannot be used in a sensor where you've got, for instance, just a freestanding current sensor that's designed to be used to sense bus bar field. Here I'm going to talk about it because it's most easily understandable, I think, in the context of angle sensing. So if I want to sense the angle of this magnet here, I am going to have two orthogonal. We'll call these Hall cells, vertical Hall cells for now. Two orthogonal Hall cells, and one is going to sense the x, and one's going to sense the y components of the field. And if I do an arctangent of the amplitudes of these, I get back the angle. And here's that equation. If I apply an external field, and this external field right now looks like it's completely in the y direction, it's not meant to. It can be in any arbitrary direction. But the output of this part is going to have an error because now instead of doing the arctangent of just by bx, it's by plus the y component of the external field and bx plus the x component of the external field. And so I'm going to get an error, which is the arctangent of the external field over the target field. So one way to correct that error would be to just try to increase the size of your magnet or decrease the air gap to make your target field super, super strong, so your signal to noise ratio is better. But that means you have to have either, hey, you have to have a bigger magnet, you have to have more control over your mechanical tolerance stack up. It's not always so easy to do that. What we can do is instead of using these two vertical orthogonal Hall plates, we'll use the planar Hall cells like we talked about early in the presentation. And now this field here, we were assuming the field comes out, curls around, and we're sensing the in-plane portion of the field. Well, this field still comes out and curls around, but now we're sensing the orthogonal component, which happens because it's curling down and then back up. So for instance, this Hall plate, I think it says BX2, would see a field pointing downward or would have a negative value. This one would have a positive value. And as we rotate, you'll still get this sine cosine, but each of these two Hall plates will see an opposite field. So now we're going to do that same arctangent, but normally the arctangent would be BZ4 minus BZ2 over BZ3 minus BZ1. And if I add the external Z component to each of these, notice that now I'm going to subtract because it's in parentheses. So now this is B external Z minus B external Z. It cancels out. B external Z minus B external Z. It cancels out. Here you can kind of see what I'm talking about. This is the field pointing down. This is the field pointing up. If I were to rotate this magnet, this is the Z component of the field mapped, by the way. So if I were to turn this magnet, I would turn this entire graph with the magnet. Um, and so because we're canceling here and we're canceling here, the error is zero. So the external field has absolutely no effect. A little bit of a caveat. We're assuming that's a homogeneous magnetic field. In other words, this function is getting raised or lowered completely by the external field. If it's a gradient magnetic field, then we've got some other tricks we have to play. But again, I could write an entire, I did do an entire webinar on differential sensing, so look that up. So this is an interesting technique that we use, and it's much easier to do this with Hall cells than it is to do it with magnetoresistance because all the bridging and all the things that have to go along with the magnetoresistance. Okay. I'm going to finish out with one last slide, and that is this is my favorite love letter to data sheets. Uh, we try very hard at MPS to write our data sheets and make everything as obvious and as um, intuitive as possible. I don't know that we're always successful. We sometimes there are things that it's very difficult to encapsulate all of a real application in a data sheet that uses characteristics pulled from a laboratory test. I mean, it's the reason why all of our customers do a good job, if I'm honest. And some suppliers do better than others, but this is a common theme that I've seen in the industry if I look at data sheets from various suppliers. Data sheets generally assume a perfect magnet in a uniform magnetic field, a zero mechanical tolerance stack up. Unfortunately, when we're working with angle sensors, we often have a mechanical engineer in the meeting, and they tend to bristle at having a zero mechanical tolerance stack up. Electrical engineers usually are fine. Lab grade power supply, no PWM, no DVDT, no EMI. We're in a nice 25-degree lab environment, and we're far away from any intrusive magnetic materials. Um, so these are the specs that are based on these kind of implicit assumptions often, and you have to watch. So sensitivity, often measured at very small signal, whereas sometimes you're going to need to have large signal. And we go back to that sigmoid curve that I showed, I think in my second or third slide, where we assume they're linear because in the small signal you got that nice linear region, but then they saturate out. And so we have to be careful. We have to make sure that we understand what our actual max and min B field is going to be. Noise density sometimes ignores system level noise. Linearity assumes no saturation or cross-axis coupling. Offset drift, often quoted against temperature, but without mechanical effects. And bandwidth, again, we have the habit of measuring small signal and then assuming that large signal will behave the same way. In real life, we've got multi-axis rotating non-uniform fields, PWM edges, magnetic tilt, air gap variation, mechanical runout, ground bounds, temperature gradients, and there's generally the magnetic sensor is not the only thing that exists on the PCB. There's steel, there's copper, there's currents. Um, so I tried to boil this down to four basic points, and like I say, it's the reason we build prototypes. Generally, outside the lab, temperature drift beats noise. So if you're in an automotive application, it's going to be like minus 40 degrees Celsius to 150 degrees Celsius. Pay attention to temperature drift. Like I said, at MPS, we do a good job of characterizing that, but it's not always obvious. You have to actually look at the numbers and apply them mathematically so that you know what your actual INL and resolution will be across all temperature and offset. Mechanical tolerances matter more than sensor specs. This is something that's difficult. As I'm an electrical engineer, I never once gave a thought to mechanical tolerancing until I started my job at MPS doing magnetic sensors. It's hugely important. Magnetic fields die off with the square of distance, and if you change that distance just a little bit, things change a lot. The field, not only amplitude, but even sometimes the direction can change a lot. So you really have to work with your mechanical engineers and understand what your mechanical tolerance stack up is, and then simulate and then actually test in real life what the effect is going to be on your system. If you find the perfect sensor, and I've got plenty to sell to you, it's going to show you all the flaws in your magnet. We assume that a magnet, when I buy a magnet and it says it's diametrically magnetized, that magnetization is perfect and the it's in line, and that's just not the case. Magnets are not perfect. And so at the very least, you need to find a magnet supplier that will give you a spec that they test to and say, hey, we're not going to give you a magnet that's outside this spec. And then you need to simulate the corners of that spec and find out what that's going to do to your linearity um, and your resolution when you're at those corners. And then the last, one of my favorite professors in college used to tell me the universe is the best simulator. And it's never been more true than in magnetics, especially if you're going to run finite element analysis. A small setup mistake can have huge. You have to verify your simulation with a real world setup. And so the biggest advice I can give is at some point you're going to have to build a lab prototype or something and actually test this stuff and see what happens, and you'll be surprised more than you expect.
Thank you, Ted and Brian, for hosting this great and interesting topic. Have a great day.
Thanks.